name's Kevin Whitty. I'm a professor in chemical engineering, been at the University of Utah since 2001. I currently teach the senior process design course. Next year you'll have that. It's a two-part course, 1 and 2. And I teach part 1 in the fall, and then part 2 is taught by Professor Dev. I do a lot with process design research. I build and design, plants. I worked in industry before coming to the University of Utah and kind of understand how things get put together. Professor Zengel has asked me to teach today. I know you guys are learning all sorts of things about fluids and doing lots of calculations by hand. We're going to not do that today. We're going to spend a little bit of time in ASPEN Plus, which is one of many simulation programs available for designing chemical plants. And we'll focus on things related to fluid transport. Have you guys been exposed at all to ASPEN Plus yet? Nada? Nothing? Not in 2800 last year? Okay, I used to teach that course as well. I love that course. That's my favorite course of the whole curriculum, because I think that's where you really start differentiating yourselves from chemists and other things. Alas, I don't teach that anymore. So I haven't ever taught fluids either. I've taught heat transfer in the past. So, but I have a great appreciation for fluids, and what we're going to do is show you that there are tools to make all of this type of work that you've been doing by hand easier. However, it's important to understand the fundamentals and to be able to have an intuition when you're using that type of software for whether or not something makes sense, right? So what we'll talk about is I'm going to go through an overview. It is a massive, massive program. ASPEN has been around, like its roots are even from when I was an undergraduate in the mid-1980s. The very first process simulation software started to be developed, and different companies were working on different things, and they merged and kind of ended up with what's today ASPEN Plus. And even ASPEN Plus, there are different components to it, but we have a pretty good suite of those components available at the university. So if you go to the ICC and you log in to the, the pool there, one of the options is ASPEN Plus. So we will go through some of that. I'll give you a kind of big picture overview, and then we'll dive into some of the issues related to specific components that are useful for fluids. So we'll go talk about flow of fluids through a single pipe. Doesn't sound real complicated. Professor Zengel sent me some of the homework that you've done previously, where you had to work out things like pressure drop due to frictional losses, or maybe pressure increase. Well, I guess pressure drop, but high pressure at the bottom of a column of fluid. So if you're pumping something uphill to a higher elevation, you have a decrease in pressure associated with that as it moves up. Talk about flow of fluids through pipes of varying properties. So if you have elbows and T's and valves and all those kind of things, you remember learning about that. ASPEN can do that type of thing. We'll talk about valves and pumps, or pumps and valves. And then just maybe, if we have time, a little bit on gas compressors. So let's dive into it. I'm just going to hop right over to the ASPEN environment. Okay, when you fire up ASPEN, this is what it looks like. So it opens up like this, and I've chosen new, and already you see that it can give you different templates, and the different templates are for different applications. And what the templates do is they select the properties database that is most appropriate for the type of problem you're dealing with. So you probably remember from thermo and other classes that there are all sorts of databases and correlations and relations for predicting properties, things like that, particularly when you have mixtures of things, okay? Things will interact and it'll change the properties of the overall mixture. So what we're going to do is we will deal with chemicals. That's a pretty simple one. And you have the option of batch polymers. We're not going to do that one. And you have, oh no, let's see if this is going to work for me today. I might have to reload this. Let's try this. Oh. Okay, let me dive out of here for a sec. Maybe. Dun, dun, dun. All right, there we go. Yay. Chemicals with English units, and down here you can see you can choose metric units or English units. We're going to go with English units just because that's what I saw the homework seemed to deal with mostly. And then you take open, and it just starts a new simulation for you, a new file, if you will, or a new project. And there are a couple of different environments here. So down here you see there's the properties environment. So that's where you enter the materials that you want to deal with. And ASPEN has this tremendous library of all sorts of things. We'll go through some examples here. And then there's the simulation environment where you'll spend most of your time. And that's where you like build the flow sheet. You've probably seen these to where you can have really exotic, chemical plants basically. And that's what I teach in my class is how to start developing those. And we do some stuff by hand, some stuff simulation work. And then the second part of process design, it's almost entirely focused on ASPEN. And you might end up with a flow sheet that has, 10 pumps and 4 distillation columns and 3 reactors and a bunch of heat exchangers. And getting all of that to balance is challenging, particularly when you throw in things like recycle, right? So you have a process and maybe your reactor doesn't get to 100% completion. Maybe it's 80% complete. So you have some unreacted reactants on the end of that. So then you want to do some sort of separation and recycle those. And usually when you recycle them, you're bringing them to a part of the process that's further upstream, so higher pressure. So you need a pump or compressor or something like that. So all of this gets baked into what you'll be learning about next year. Today we're going much more simple. So here you can see that you can specify the components. And it's reasonably intelligent. If I put in water, it knows water. We would hope that it knows water. If I put in like, give me something bizarre. Toothpaste. Toothpaste. Uh-oh, toothpass. All right. So this is something that I think is horribly unfortunate about ASPEN. And other software programs don't have this limitation. But you remember I was saying how ASPEN was based on stuff from eons ago? Okay. For some reason, all along the way, they have never updated from, honestly, the DOS, like
16-bit error?
Well, it's not the 16-bit error. It's even worse than that. You are limited to 8 characters in naming things. Okay? Which is in my view, completely unreasonable today. So that's why it ends up being toothpass instead of toothpaste. And we'll see if ASPEN knows what toothpass is. And, wow, it took it. I wasn't expecting that at all. But you can see it like doesn't know what it is. It doesn't have a formula or anything like that. So I'm actually going to go ahead and delete that guy. And we'll actually, just for today, we'll leave it only at water. You can do find. So if you are looking for something like, oh, what's your favorite bizarre chemical? Polyethylene glycol. I'm glad that someone has a favorite chemical. We all need our favorite chemicals. By the time you graduate from chemical engineering, you will have your favorite chemical. So if I say polyethylene, let's see if I spelled that right. And then we say find now, and it churns for a bit. And dimethyl ether polyethylene glycol. I'm not going to go with any of those, but you can see that that's kind of the function. If I put in glycol, it'll spit out a whole bunch of them. And then you can just add it to the list. So it's there. Now you see it's got like a whole ton of them, and one of them is undoubtedly polyethylene glycol. I'm not going to bother going through it, although I saw ethylene glycol there. LMNO. Yeah, ethylene glycol was on there. Maybe that's what we want. So you can see there's different versions of that. I'm not going to add any of those, but now you know that if you need things like that, that's how you find them. So we'll go with just water. Aspen has this nice thing. It's kind of hard to see. So here's a larger version of it. Next. So as you're going through setting up your simulation, there's that nice next button, right? And you click that and it brings you to whatever that next step is. I am actually going to add something else. One of my favorite chemicals is okay, ethanol. And the reason I put that in there is because what I'm hoping happens is when I click next, it will ask me this. So it's doing a binary interaction. So you remember that I said earlier that the property databases recognize if you have like multi-component fluids, and we all know that ethanol and water have this relationship. There's an azeotrope and things like that associated with it. So I'm going to go ahead and say, yeah, you can actually click next over that. And you can see the options, run analysis setup, da-dee-da-dee-da. I'm just going to go to simulation environment. You can see the types of things that are here under the properties database. I'm not going to bother going through it, but basically, you tell it the chemicals you want. You can give it unusual things. So if you had a process where you were using sewage sludge, right? So when we run our garbage disposals and flush our toilets, all of that goes somewhere, right? And then they filter out the solid, the sludgy part of that. And you can use that as a fuel. You can burn it, things like that. If you were doing that in Aspen, Aspen doesn't have one called sewage sludge, and every sewage sludge is going to be different, right? So what you would do is send it in for analysis and get the carbon, hydrogen, oxygen, sulfur, nitrogen, all that kind of stuff. And then maybe also the energy content. There are labs that will analyze that for you. So then you can actually add your own material, and you put in all those properties, and then Aspen can run with that. I'm not going to bother going through that today, but you should know that functionality is there. So I'm going to go to the simulation environment, which is here. And let's spend a little bit of time here. This is where you actually build the flow sheet. So it's kind of a graphical interface, which I think could use some updating, but I'll leave that. So you see all these different types of things at the bottom here. There are mixers and splitters. A mixer is, you would think that it's something, where you bring two fluids in and then there's, stirring and whatnot. It's not that complicated. It's actually just if you bring two streams together and mix them. So it could be just a T in a pipe, right? You've got a stream coming in here, a stream coming in here. They combine and exit. The way that Aspen does the calculations, it needs you to tell it if you're mixing streams like that. So that's all that is. A splitter is just the opposite. Maybe another T, and then you just tell it like 75% is going this way, 25% is going this way. All it does is just proportion them. The compositions are exactly the same, the temperature, pressure, exactly the same. It just splits it. And then there's a solid splitter. Then we've got separators. So there's flash drums, decanters. That's just if you would have maybe a flow that's got some liquid and gas in it, and it'll just separate those phases. Exchangers or heat exchangers, you have heat transfer next semester, I believe, and you will learn everything you ever wanted to know. No, that's not true. You won't learn everything you ever wanted to know about heat exchangers in the next class. You'll learn the theory of everything that you ever wanted to know about heat exchangers next semester. Do you have it now? Heat transfer. So when do you have that class? What time?
Like 12.
Oh, okay. And that's with Professors Powell and Pershing?
Yeah.
Just Pershing, okay. Oh, that's right. Powell's on sabbatical. Lucky him. Okay, so you're learning a lot of theory. I'm assuming that you have learned all you ever wanted to know about convective heat transfer coefficients and the capital U and working out the area of a heat exchanger and whatnot. And you might have even been exposed to Promax.
Yeah.
Okay, so Promax and Aspen are both process simulation type systems. Promax is better for heat exchangers, which is why we teach Promax. And you've seen in Promax, the interface allows you to do things like have more than 8 characters in the name of something, and it's color-coded and whatnot. However, Promax is not overall nearly as robust as Aspen. Aspen is kind of the gold standard, even though it's kind of wonky in its own ways. So, but it's good for you to recognize there are different simulation tools. So there's Promax and Aspen are the main ones that we use in this department. but there's probably another half dozen out there that, some of them are very niche and they work for, if you're working with polypeptides or something like that, it has its own process simulation software. Okay, so these are heat exchangers. And it'll do the same type of thing that you're learning in heat transfer. However, these ones will actually design the physical unit. So now you're learning like how much heat transfer area do you need, right? And maybe you come up with a heat exchanger that needs 15 square meters of heat transfer area to achieve the level of heat exchange that you want. But you probably haven't got into, okay, what does that look like? How many, maybe you've gotten to how many tubes, what are the shape of those tubes? How many passes are there? Does it have a floating head? Is the shell side, distribution, does it come up or does it come down? Does it split? All that kind of stuff you can work out in ASPEN. And next year, when you take the design course, we'll spend a good bit of time kind of walking through the physical design of a heat exchanger. Same thing with pumps. Have you spent much time on pump curves in this class? Okay. Yeah, so it's an important thing to understand that for centrifugal pumps are kind of, I always describe them as a fan for liquids. That's not really quite doing it justice. But the key is that if you have your centrifugal pump and you put and it's turned off, let's say, and you put a bunch of pressure on the outlet to that, you can actually push fluid backwards through the pump just because it's not like super tight tolerances. And because of that, you sort of have slip around the impeller. So as you increase the flow rate, and particularly the discharge pressure, then that slip increases. So it's not exactly linear in terms of the performance. So that's why it kind of curves over. And when you are designing a chemical process, you need to be able to choose, an appropriate pump, recognizing that it's got this curve and this shape. But anyhow, we'll spend some time on that. We won't belabor heat exchangers. Glad to hear that you've got it in ProMax. Columns, I'm actually teaching this in my class right after this. Just distillation columns, basically. And again, I never remember what order, the classes are. When do you take mass transfer and separations? Next semester. Okay, I think they flipped that. I think it used to be that heat transfer was spring. Anyhow, in that class, you'll learn about distillation columns. And it's basically non-reactive separation of components. So a lot of processes where people are targeting making an alcohol, it's a catalytic process. And you might be targeting propanol, like the C3. But just the way the process works, you'll actually end up with some methanol, some ethanol, some butanol, all these other alcohols. But if you want just the propanol, you have to distill it. And maybe it's a multi-section distillation column, or maybe it's sequential distillation columns. So we'll go through that, not only the performance of them, but the actual design of them. How many trays do you need? What the trays should look like? How big of bubble caps should you have? How tall of a weir do you have to set the liquid height on the tray? All that kind of stuff. So we get into kind of more the physical design of things next year in design one. So we're not going to talk about columns. Reactors, that's another big part of it. And again, when are you taking chemical reaction engineering? Is that next semester? Okay, that's a great class. I like chemical reaction engineering. So there's all sorts of different types of reactors that you can have in ASPEN. And then there's this weird one that they just classify as pressure changers. And that's actually where we're going to spend some time today. So in fluids, you are changing the pressure of things. And let's look at it. You've got a pump. A pump obviously will increase the pressure, and pumps are really important. And then there's a compressor, which is same type of thing, but it's for gas, right? And there's different types of compressors that ASPEN has. There's M compressor, which is a multi-stage compressor. You remember from the ideal gas law, PV equals nRT, if you increase the pressure of something, it's also going to increase the temperature of it. So if you're taking air, room air, and you want to compress it to 100 atmospheres, which is pretty high pressure, that's going to be a really, really high temperature, right? You guys can crank out the calculation in your head and see that it's like over 1,000 degrees. So what you do is you do a multi-stage compressor with intercoolers in between each one. So you maybe increase it from 1 to 4 atmospheres, so a compression ratio of 4, already the gas is heated up quite a lot there. Then you run it through basically a heat exchanger, cool the gas back down. Then you go from 4 to 16, and then maybe 16 to 64, and then eventually to 100, whatever. But after each of these stages, you have an intercooler to cool things back down, which is good because a really, really hot gas is not very dense, and the efficiency of pumping or compressing or whatever improves the more dense the material is. Okay, so that's a multi-stage compressor. Valve, I mean, valve sounds so boring, right? I mean, it's like a thing you close and open. But there's a lot more to than that, particularly process control valves used for adjusting the flow rate of something. Those are typically, like if you look at the body and what it looks like inside, it's usually what's called a globe valve. So it's not just like an open-closed ball valve. So we'll talk a bit about valves today. Pipe sounds really boring. And normally in Aspen, you wouldn't actually use a pipe to connect things. I'll show you use streams to connect things. Aspen will usually assume that pressure drop between things is negligible. So if you have a chemical plant, hopefully you've all toured a chemical plant at some point or other, and you see that they, all the different units are pretty close to one another. And the pressure drop, you size the line so that it's fairly marginal. So you don't have to do this pipe between every process unit. However, if you do have something where it's going to be a longer distance, or maybe you're sending water to a tank that's way uphill, or vice versa, something like that, then you can use this pipe, and we'll spend some time on that. And then pipeline is kind of the same, but it's just a little bit more complex configuration. There's this thing called manipulators, which I won't spend time on. It's almost something in Aspen to allow it to do the calculations. The one that is useful, and we'll talk about this next year, is this duplicator. So a duplicator is if you want to do like a what-if scenario, and you say, okay, I want to take this process stream and I have a couple of different alternatives for how I can, process it, heat it, react it, whatever it is. Or maybe with distillation columns, there's a lot of flexibility. And you say, well, maybe I want to have, if I have a 3-component system and you want to separate those 3 components, you actually need 2 distillation columns usually, right? The first one, if you have A, B, and C, maybe the first one will separate out A and the second one will separate B and C. But alternatively, it could be that the first one separates out C and the second one separates out A and B. So maybe you wanted to test those 2 different configurations on the same stream. You can use this duplicator block. And what it does is you have an input block and it just duplicates it, and you have 2 or more output blocks. And they're exactly identical. So with that block, you've totally fried any mass balance that you ever had, right? Because you have way more stuff coming out than going in. But it's useful for doing that type of analysis. Figure out what you want, delete the other ones, and go with that. And I'm not going to bother going through the rest. You see there's solid separation, things like that. All right, let's go back to these pressure changers. And I'm going to start with the easiest one, which is a pipe. I know this was one of the homework assignments that you had. And in this, you have a long section of pipe. I'm not going to remember this, so I depend on you with your better memories than me to remember this. Water at 20 degrees C, 2,000 feet of pipe, 120 feet rise, 3 cubic feet per second, and diameter 6 inches. We're not going to bother with the pump quite yet, so we're just going to focus on this pipe and work out what the pressure difference across the pipe is. Okay, so remember those numbers because I'm going to ask you for them again. Just because I don't feel like dashing back and forth between the environments. So I'm going to choose pipe, and you just click pipe and put it in there, and it wants a name, and I'm going to call it pipe because pipe has less than or 8 characters or less. Okay, it's a very small pipe, so I'm going to grow it here. So that is pipe, and then the other one is material. And if I click the little arrow here, you'll notice that there's actually a few different types of material. So there's what they call material, right? Which would be a gas or a liquid. It could be solids, whatever, something that you actually are moving. But the other ones there were heat, okay? Let's see if I can click that. Oh, work with me. Oh, I didn't mean to do that. I have happy hands. So heat and work are also things that you can put in. So maybe you have a combustor and it's generating a lot of heat, and then you want to use that heat to warm up some other process. It's not quite a heat exchanger, but you can basically link the heat from one to another. We're not going to bother with that today, but again, just so you know it's out there. So I've got a material stream, and I'm going to click here, and then I will connect it here. The little red arrow means that you can connect it, and I'm going to call it in. And then from the outlet, we have another stream, and creatively, I'm going to call that out. Okay? Then in ASPEN, you remember we have our friendly N, the next button. It's up here, it's very small, but it's up in the toolbar. So I'm going to click N, and it will ask me some questions about things. So what it's asking about is in. It wants to know some information about that stream that's coming into our pipe, okay? And we can give it temperature and pressure. We could also give it vapor fraction. That would be if you have steam usually, but we're just going to go with temperature and pressure. And do you remember what that temperature was? 20 degrees C, right? I even remember that, so I'll put in 20 degrees C. You weren't given a pressure, but what I'm going to do here is, this would be like after the pump, so we're just focusing on the pipe. I'm going to give it a very high pressure because I want it to calculate the pressure drop. If I said like 15 psi, already you know that because it's at the bottom of that 120-foot rise, it's got to be more than 15 psi. How many psi would it be at the bottom of a 120-foot column? In my class, I ask the class questions like this all the time because it's a valuable skill to be able to ballpark things. Roughly.
75.
Yeah, that's not too bad. No. 75 psi. All right. Another important number to know. How many feet of water is in one atmosphere? So if you're in a deep swimming pool and you were to go down some certain distance, eventually you get to where the water pressure is 1 atmosphere, 14.7 psi. How deep is that? Let's ballpark it, okay? Is it closer to 1, 10, or 100 feet? 10-ish, okay. Then is it closer to 10, 20, 30, or 40 feet? 30, okay. It's 33.9 feet, call it 34 feet. So if you go down 34 feet, that's 1 atmosphere. So how many times does 34 feet go into 120 feet? Roughly. I want one significant digit. 4, right? How many psi is that? 60, okay? So, and maybe add on a little bit. So maybe it's like, 55 or something like that because you divided by 34 instead of 30. These types of things are useful to be able to do in your head. You got to remember all these wonky translations, but 34 feet per atmosphere. How many inches of water per psi? Have you talked about inches of water at all as a pressure unit?
No. We did a conversion once, and then it's like, this is wonky.
It is, but you see it used all the time. And where you see inches of water used is in things like pressure gauges and differential pressure across orifice plates and things like that. There's a historical reason why they use inches of water. And an inch of water is actually a pressure unit. You would think it's a length unit, but it's like millimeters of mercury, right? You're familiar with that? So it's same thing, but now it's inches of water. So if you have, a glass of water with an inch in it, the pressure at the bottom of that is 1 inch of water. There are 28 inches of water per psi, okay? And 14.7 psi per atmosphere, so you can do the calculation. So it's useful if you have very, very small pressures. But the reason they use it at all is back, when chemical plants were being built 100 plus years ago, they didn't have all the cool electronics like we do to measure things. So if they wanted to measure the pressure drop across an orifice plate, they would actually use either a manometer or what do you call it when it's a dual-sided? But you understand what I mean. To measure the pressure difference. And you would actually look at it. And on the high side, it would be lower because it's the gas pressure on the top, and on the low side, so you'd have this pressure difference, and you'd say, oh, that's 6 inches. 6 inches of water pressure difference. And then you can calculate that out. But anyhow, that's why they use inches of water. So back to this, I'm going to put a high pressure. We calculated that just due to the rise, it would be about 55 psi, 55 or 60. But then there's pressure drop because of frictional losses through that pipe. So I will say, I don't know, to use a round number, I'm going to say 1,000, which is way higher than it needs to be probably, but we'll leave it to that. Okay, so now when I put in 1,000, here you see this little thing is still red. Okay, that means that I haven't given it all the information that it's needed. I don't need to put in the vapor fraction because I didn't choose that up there. I'm going to do a total flow basis, volume, and what do you remember what that was?
3 cubic feet per second.
Right, 3 cubic feet per second. Let me put on my glasses because I am old. Cubic feet per second, okay? And we will see 3, so it's getting there. And then we need to tell it the composition of that. So I'm going to do it on a mass fraction basis, and I'm going to tell it it's 1 of water. So I've told it basically it's 100% water at 3 cubic feet a second, 20 C, and 1,000 psi. Now you see that little red mark turned blue. It's a check mark. It says, good, we've told it everything we want. What do we do next?
F4, next.
Okay, we're going to do our next button. And now it's asking us about this pipe, okay? So we're going to say it's fluids flow, not solid conveying. Do you remember how long the pipe was?
2,000 feet.
2,000 feet. And the inside diameter of the pipe, it wanted it in inches, so I'll put inches. And we're going to say 6 inches. Do you know what pipe schedules are?
Yes.
Oh, you do? Did you learn that in this class?
Mm-hmm.
Oh, good for Professor Zengel.
You know why measurements they are? No. We go ahead there.
Well, I mean, it's you know, in sophomore and junior years, you learn a lot of theory, and in this class, I'm sure you're learning like Bernoulli's and all that kind of stuff. But many of you, I would argue that half or more of you, your first position when you exit the university will be something called like process engineer. And when you get working with a company and start designing chemical processes, there's all this practical stuff that you need to know that you aren't really taught very much in the early years. I try to cover as much as I can in my course. But pipe schedules is one. So again, it's the United States just loves to be different than everybody else. I blame England for this, right? That if you go to a country that has totally adopted the metric system, and they would say it's a 20 centimeter pipe, you can measure something on there and it's actually 20 centimeters. In the US, if we say a 6-inch pipe, and when I say 6-inch nominal pipe, that's like what it's called if you're using the pipe schedule. So if you go to Home Depot and you buy a 6-inch pipe and you take out your tape measure and you're going, oh, what part of this is 6 inches? There ain't nothing on that pipe that's 6 inches. I mean, it's true. A 1-inch pipe, the outer diameter of a 1-inch pipe is 1.3 inches. Okay, and then you've got the schedules of the pipe, and the schedule is just the wall thickness. But even that, the common one, you go to Home Depot, you buy a 1-inch pipe, it's probably going to be what's called a Schedule 40 pipe. That's the standard size. There's nothing 40-ish about it. It's not 40 thousandths of an inch or 40 millimeters or anything like that. It's just what it's called. Anyhow, so ASPEN has all that built in. So if instead of telling it an exact diameter, I could use pipe schedules, and it would ask me the material, okay, and I'm going to say it's stainless steel. I'll say carbon steel. And then schedule, okay, these are the different schedules. 40 is the standard one, and then the nominal diameter is 6 inches, so I'm going to go with that. Okay, you see that its inner diameter, it calculated 6.065 inches, so it's close to 6 inches, but not quite. I'm actually going to run with that one just because it's fun. Okay, pipe rise. Do you remember that? 120 feet.
You have like the height difference between like the tops of the tanks of water, not to say the pipe rise.
Yeah, and I was looking at that problem statement, and to the life of me, I couldn't figure out what the actual pipe rise was, just the way the problem statement. So let's go with 120 feet, just to have a number in there so I can show you this. What time does this class end? 20? 25, okay. And then you can put in things like roughness. It has some default numbers, but even with this, we're good, right? That has turned blue, and so if I take next, it will say, we're all happy, can we run the simulation? And I say, yes, please run the simulation. And then it goes into like all this DOS stuff. So like put on your best 1980s or 1970s outfit and, go through this. And it's done. Okay, so it's run the simulation. Over here where you've got the tree, so one of them is for streams, one of them is for blocks. Whoops. So blocks are the different units, the reactors, heat exchangers, pumps, all that kind of stuff. So you have streams, and you can look at the properties of the streams. You can look at the blocks, and we've got the one block is pipe. So you see the little exclamation point there? It's given me a warning. I know what this warning is. I'll tell you what it is. Is just the way this works. It's kind of defaults to two-phase flow, vapor liquid, but we've only got liquid. So it's a warning. It's saying, are you sure there's no vapor in there, effectively? I'm going to ignore it because it still solves. Sometimes you'll get an error. When you get into these big, massive spreadsheets, you get errors sometimes that are really hard to trace down, okay? This is easy enough. We don't have that. So let's go back to our main flow sheet. And we'll ignore that warning, and you can see that we can put in temperature, and we can have it show pressure. So here it's 1,000 psi at the front, and at the back end, so 850. And that is due in part to the rise, but also just due to the frictional losses, okay? So let's go to this block, and we're going to go to the pipe block, and we'll expand that. And we're going to go to the results tab, and it gives us all sorts of information. So the total pressure drop through there, ASPEN loves to calculate out things to a zillion digits, right? In my class, if you use more than 3 significant figures, you get dinged. The one I love is when we're doing things like, what is the flow? And someone will say something like, it's 146.189722384 kilograms per second. And you're going, okay, so that's like nanograms out there, like at the far end. So anyway, in your reports, don't go overboard. Don't just copy that number. What would you use instead of 146.766209?
147.
Yeah, 147. We'll call it good at that. Okay, so it shows you the different components of the pressure drop. So we had estimated 55-ish. It ends up being 52 psi, okay? And then the frictional pressure drop actually exceeds that. 2,000 feet is a very long piece of pipe, okay? And if you have a 6-inch pipe, okay, good, it doesn't show that. 6-inch pipe, again, ballpark, 3 cubic feet per second. What's the velocity through a 6-inch pipe? Yeah. This is fun. We should just have a class that's doing this kind of stuff. And you're like, almost like a game show, right? So 6 inches is half a foot, right? And then half a foot squared is 0.25 times 3.14 divided by 4, right? Gives you the cross-sectional area. So 0.25, I'm going to call it 0.2. So 3 divided by 0.2 is 15. 15 feet a second, something like that. I think one of these can actually show it. Is it here under profiles, pressure, temperature, velocity 14.9. So you can get pretty far just think about these types of things. Just like ballpark them in your head, learn a little bit of geometry. Okay, back to the summary. Okay, and when I say learn a little bit of geometry, I don't know how to teach this. Please, when you take my class, know that the outer, like, surface area of a pipe, we're doing heat exchangers, and I say, okay, what's the surface area of a pipe? What is the formula for the surface area of a pipe?
Pi d L.
Yes, pi dl. It is not pi r squared L. First of all, that gives you like wrong units, right? Yeah, people are doing like the volume is what that is. Anyhow, we just had an exam, and I told them like in 7 different languages and right before the exam that this is how you calculate the surface area of a pipe, and still like 30% of the class was doing the volume. All right, but you guys are smarter. Don't tell this class. Okay, so that's the pipe. So now let's go back to the setup on the pipe. And one thing that you can add is you've got fittings that you can add. So you can tell whether it's flange welded or if the pipe is just screwed. Okay? So you've got gate valves, butterfly valves, blah, 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 blah. And you just tell it how many of those there are. And I know you've done this in fluids, and you end up with your equivalent length, right, associated with that type of fitting. It can do that. You can throw in this miscellaneous one. And then there's the second one of different types of fittings. You've got enlargements and contractions. I know that one of the homework problems on that assignment had something where you had an expanding cone going into a tank, and you can add that kind of stuff. I'm not going to bother going through that now. It's like super simple. You would just add that to the pipe, rerun the simulation, and it would come up with the right answer. Okay, 2 other things that I want to cover in the 8 minutes that are left, but we're very efficient. So we're going to go back to this main flow sheet, and I'm going to get rid of the pipe. Bonk, maybe. Okay, we're going to delete Mr. Pipe, and we're going to add Mr. Pump. Okay, so here's a pump, and what should I call it? You guys are good. Okay, then when we go here, we're going to go to this stream. I'm going to right-click it, say Reconnect Destination. Dunk. Okay, and I'm going to put it on there. Bonk. And then on this one, I will reconnect the source. Same thing, right-click it, and I have to look on my screen. I actually, you would hit, like if you have a full keyboard, you would hit the delete key on, I have a Mac, and I have to hit function delete, or you can right-click and delete is one of the options. Okay, so now that's happy. So I'm going to hit next. And actually, I'm going to do a quick change on this guy. I don't want 1,000 PSI coming in. I will say, I'll say 100. Just change that. Then I'm going to hit next, and it asks me about, should ask me about the pump. Actually, click next. Okay, there we go. Here's our pump, and it's a pump or a turbine. It's almost always going to be a pump in this regard. A turbine is kind of the inverse of a pump. If you want to generate power from a fluid flowing through it, then use a turbine. We're going to use a pump. And then you specify whether you want to do the discharge pressure or the pressure increase or the pressure ratio, blah, 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 blah. I'm just going to choose discharge pressure. That's the most common one. We have it coming in at 100. Let's say it's exiting at 500. Okay? So then we take next, and it should be happy. Yeah, I mean, pumps are really easy. Okay? So now let's go back to our main flow sheet. It has run, and you see it went from 100 to 500. Now we go to our blocks, and we go to pump, and we go to results, and it tells us how many horsepower that pump needs to be. So 314 horsepower. One thing I forgot to mention, and this was in the problem statement, is if I scroll down here, you can actually specify the efficiency of the pump. So the efficiency is of the shaft power, not the motor power, but of the shaft power coming into the pump, what fraction of that is delivered to the fluid in terms of like increasing its pressure. So you could say something like 0.75, and then rerun it, and then go back to your pump results, and it's still, the fluid power is still the same. Brake power, brake horsepower is the shaft power, so that's fluid power divided by the efficiency that we put in. The electricity that would be needed for the motor, it just recomputes it, pressure change, all that kind of stuff. So you can see all this type of information. One other thing on the pump that we could do, and I don't actually know if that works is you could specify a particular type of pump. For fear that this is going to crash me, I'm not going to click there. But what it does is it has a data bank of different pump manufacturers, different pump models. It'll bring up the curve, like this pump curve, and you can actually specify, rather than kind of a generic pump like we had here, you can specify a particular pump. All right, now let's go back here, and I'm going to maybe relocate this guy here. And the last one I'm going to throw in is a valve, okay, which I will call Hank, just to give it a name. We need to add one more stream. I'll just call it out 2, and then I'm going to reconnect this stream to the valve. Okay, then I hit next, and it's asking now for the valve properties, and it wants to know how do you want to calculate over the valve? Is it an adiabatic type thing, or do you want to calculate the flow coefficient for a specified outlet pressure? You probably haven't gotten into flow coefficients on valves, so basically the flow coefficient, if you have a control valve, it kind of, the number, what it means is the gallons per minute of water that would flow through the valve for 1 psi pressure drop, okay? And the numbers range from fractions to hundreds, okay, depending on the size of the valve. So if you have a little teeny tiny valve, that's going to have a small flow coefficient. A massive valve, it's a big flow coefficient. And it actually depends on kind of the internals of the valve. You can have what looks like a big valve, but it's a little tiny inside or something. So for now, I'm just going to run this adiabatic flash, and you would specify the outlet pressure. So we know now it's coming in at 500 psi because we've pumped it up. Let's bring it back down to 100. So this is like a horribly inefficient process. All we do is like pump it up to high pressure and run across a valve to get to the low pressure. Valid phases, it always defaults to this vapor liquid. I'm just going to go with liquid only. And I think it should be happy. So let's run that. Oh, what's it? Oh, you know what I did? I need to fix my pump. Where is the pump setup? I had clicked that, but there we go. Now we'll run it. Okay, and if we go back to our main flow sheet, you can see it went 100, 500, 100. And then if we go to the valve, which we called Hank, so if we go to Hank's results, you can see the types of results that you get there. Works out what the outlet temperature was of it. Not so much exciting there. The other thing that you can do on the valves, let's try this, is let me go to the input, calculate the flow coefficient, and run it again. Oh, it needs the valve parameters. The valve type, will say it's a globe valve, which is what I mentioned earlier, is a pretty common one. Manufacturer, it's got one option. Series style, we'll say it's the equal percent flow. And then the size of valve, that was a 6-inch pipe, so we'll say it's a 6-inch valve. Should be happy. Run that, and now we can go to the results, and it should show the coefficient. So valve flow coefficient 67. So if you were talking to the manufacturer, you'd say we want a valve with a flow coefficient of 67. All right, we're pretty much out of time. That's an introduction to ASPEN. We focused only on liquids. You can do it with compressors as well. That takes quite a bit more input, so I didn't bother doing it today. Hopefully you find it useful. Remember all this, and I will see you next year in design.